All right, we're live now. All right, for this week, we didn't prepare any specific topic, but let's start with a small story. So, last week, I was at a dinner with a friend, and he read the article that I wrote about probabilistic versus deterministic applications, and we were talking about that. And he asked specifically about probabilistic algorithms, and that led to the question of how modern AI works. And it makes me think that not everyone, including engineers, understand the basic of uh, the concepts that led to this modern AI to emerge. So maybe let's talk about that this week. Let's really talk about the fundamentals and the principles that led modern AI to exist the way it exists today, and how potentially we can use it. So instead of being the passenger in a car you don't understand, let's really understand how the car works a little bit, and then that can lead us to certain horizons that we haven't thought about before. So let's start with intelligence and understanding human intelligence. Human intelligence doesn't come from mysterious complexity. It comes from billions of tiny, simple units we call neurons. And each neuron alone doesn't actually do anything, right? It receives signals from other neurons and decides whether to pass those signals forward or sends its own signal onward. It's simple relay. But billions of these tiny relays connected, they create impressive results. They basically form this intricate web we call the human brain. And artificial intelligence uses the same idea. So instead of biological neurons, AI uses what we call digital neurons, right? So these digital neurons are not cells, they are small mathematical units running inside computer code. And each artificial neurons takes inputs, performs simple calculation, and sends output to the next neuron. So by themselves, these units are simple calculators, but grouped together in a vast network, they form powerful patterns of recognition and prediction. And that's really what an artificial neural network is. It's thousands or millions of these digital neurons working together, mirroring the human brain and the magic of pattern finding and pattern recognition. But the neural network doesn't start out intelligent. It starts blank, like the child's mind. It learns from examples, not instructions. And to teach a neural network, engineers give it large amounts of data. So, for instance, to teach a neural network to recognize dogs, you show it thousands of labeled dog images. And over time, the network discovers patterns. It discovers the textures of fur, shapes of ears, outlines of tails, and so on. And gradually, it can distinguish dogs from other objects. It learns through experience, much like we do, noticing small clues, connecting patterns, and they basically form broader conclusions about those shapes and patterns. However, unlike our brains, these neural networks, they don't have intuitive sense. What that means, basically, they don't really know what a dog is. They only know patterns. They detect statistical likelihood, not certainties. All right, but let's go deeper. So we know AI runs on digital neurons, but how do those neurons exist physically, and what's beneath the software? So if you think about it, these neurons, digital neurons, they exist as tiny electrical switches inside computer chips. These are called transistors. A transistor is one of our simplest, but maybe the greatest invention ever, right? It's a small electrical device, microscopic, that controls electrical current. So think of it as a simple on-off switch. It lets current pass or blocks it. And with the on and off, we built the binary language, the zeros and ones. And with the binary language, we created programming languages. So with programming languages, we stacked abstraction on abstraction. So you don't have to think in ones and zeros to write your next application. But fundamentally, we are using programming languages to talk to transistors that let current go in one way or the other, on, off. And abstractions is just a fancy way to hide these complexity and make humans focus on building the cool stuff and not really flipping switches all the day. And this is our interaction mostly with these different applications. It's through these abstractions that fundamentally touches on those transistors. Now, if we put billions of these tiny switches in one single silicon chip, this is what we call basically the microprocessor, which is inside your laptop right now or your smartphone. Traditional computer chips, the CPUs, they are components that can process tasks one after the other. So they give you the illusion of having everything running at the same time, like in your current computer. I'm looking at my computer. I have the clock. I have tabs open. I have a chat open. All of those are processed by the chip in my computer. So my computer is running on the Apple M3 chip that has tens of core processing units. And I think they have over 90 billion transistors on this chip. And each core is processing tasks sequentially. That's very important to understand. And they do them in a fast way, and that gives the illusion of things running in parallel. But for neural networks, that method is not sufficient. Running tasks sequentially is not very efficient because the neural networks, they perform millions of these small calculations at the same time. So to solve this, years ago, engineers turned to graphic processing units, or GPUs. GPUs are designed to render complex video graphics, painting colors on the screen. So if I'm looking at the screens, all of those tiny pixels, they are moving in a fast way to render certain images. Those are run through the GPUs. So they are processing units that contain thousands of tiny cores compared to the CPU usually that has 4, 8, or 16 cores. GPUs, they have thousands of those. And each core handles a small calculation independently. If you think about it, this really fits the processing of approach of the neural networks. The neural networks, they need millions of simple calculations done at once, not one after the other. So, in short, transistors enabled the neurons, the GPUs, arrange those transistors in a massive parallel formation, much like the brain's neuron. And this relationship is very direct. Again, so the transistors form the basic unit, the digital neurons perform the calculation, and the neural network produce the intelligence. At the core, this is the basics of the fundamental basics that allowed neural network to exist nowadays. So with training, we train certain networks from this large neural network to process patterns, to understand probabilities about what is a dog or what is a cat or what is the next likely thing to happen. And they are facilitated through this GPU that perform all of these different calculations at once, similarly to how the human brain works. All right, let me think a bit about where we go next. Most probably interesting thing from here is either to go and understand how the decision tree happen and get rendered inside the neural network, and maybe that is in itself a separate topic. Or maybe think what's going to happen next, because in our world right now, or maybe in the last 60 years, Moore's law, which is the law that says that the computational power will double every 18 months, which was, I think, correct for the last 60 years, was built on the principle that we can pack more transistors on a small chip every 18 months, which allow us to run more tasks faster and sequentially. However, with GPUs, the expansion is different, and it's more horizontal, because if you pack trillions of GPUs or billions of GPUs, you can run or mimic large neural networks that mimic the human brain. And I think this is where we're going. That expansion is rapid, and it's faster than what we've seen with Moore's law, and probably it's going to be non-linear. It's probably going to be exponential, and that would allow us to run much more complicated probabilistic algorithms or processes faster and in parallel. All right, let me see if we have any questions, but I'll stop here before I go any deeper. Yeah, so we have here a picture that basically tells you the difference between what a CPU and a GPU is. TPU and LPU are much more advanced forms of organizing these transistors or these cores. Fundamentally, think of a GPU as having thousands of cores and CPU having fewer cores. LPU has just one core that is much more specialized. TPU is similar to GPUs basically, but it is much more efficient for machine learning workloads, which is the fundamental part behind neural networks. All right, we don't have any questions. I don't want to go deeper without losing everyone here. But in general, you want to think about the fundamentals of that led us to where we are here, starting from the transistor and how that relates to this. And I think I tried to explain that in a few minutes, but it's really going from zeros and ones, binary abstraction that led to these binary programming language to evolve into higher programming languages and paradigms that eventually are actually just programming current on a circuit to go zero, go here, or one, go this way. And that's basically it. And with neural network, we're now stacking those to run, instead of running sequentially, like what the CPU is on a computer or on your phone, now they can do multiple tasks at once. And those tasks or firing those digital neurons is important to learn certain patterns or probabilities. I think maybe next we can focus on what is the nature of the function that determine what neurons to fire next. That's the probabilistic pattern. There's a function, mathematical function, that is used in these algorithms, and these kind of algorithms that compute that probability. Is this a dog, really, or a cat, or something else? And then there's a base probability that gets you go here or here and then get the result that you want, which is this is a dog or a cat. And that function is part of the model that these companies are creating, like OpenAI, Anthropic, Google. They are basically starting from a blank neural network. They train it with data that is labeled. And then they have their own internal functions that determine these probabilities and instruct in a way. Instruct is probably the wrong word, but the function is instructive that computes that probability and tells it go here or go there. And that's at the base level how these systems work. From the outside, that's really what gives them the probabilistic nature. They are dealing with likelihood, not certainties. They are not like traditional algorithms that are instructive and deterministic and functional. So giving the same input, you will always get the same output. That is what traditional software is built upon. With these neural networks and probabilistic-based approaches, they're more giving you chances of most likely this is the result that you want, and this is the outcome that they learned. There are different techniques to improve that learning. You probably have heard about fine-tuning and distilling LLMs or models, and that's basically playing on the probabilities of certain outputs based on new data or new learning, or improving the probabilities of those outputs based on a new learning that you will give to these models. Those are also techniques to improve the chances of it producing the proper answer or the proper output, but fundamentally, they remain probabilistic algorithms. All right, we'll cut it short for now. And then if you have any questions, please ask them. This will lead us more to talk about interesting subjects. I started with a question that I had from a friend last week about fundamentals of AI. Maybe next time we go through the history that led us to where we are today, and maybe that gives us an idea of the future of what will happen tomorrow. Thank you all.